Space is vast, time is deep, the universe is young. In the grand tapestry of the cosmos, we are but a fleeting moment, yet even in its infancy, the universe holds secrets that baffle the greatest minds. Yet within this youthful universe, we find something perplexing: supermassive black holes. These colossal entities defy our understanding of cosmic evolution. These aren't your everyday black holes, remnants of collapsed stars. They are far more enigmatic, far more powerful. These are behemoths, millions, even billions of times the mass of our sun. Their sheer size and mass are staggering, dwarfing anything we can imagine. They lurk at the heart of galaxies, including our own Milky Way. But here's the catch: their presence so early in the universe's timeline is a profound mystery. These cosmic titans appear very early in the universe's history. We're talking about a time when the universe was still in its formative stages. We're talking about a time when galaxies were just starting to form. The universe was a chaotic, turbulent place with matter clumping together to create the first cosmic structures. How could something so massive arise so quickly? The rapid formation of these black holes challenges our understanding of physics and cosmology. It's a question that keeps astronomers up at night, staring into the abyss, searching for answers. They peer through telescopes, analyze data, and formulate theories, yet the enigma remains. The early universe was a chaotic place, a hot, dense soup of particles. It was a time of intense energy and rapid change, where the laws of physics were just beginning to shape the cosmos. Gravity was just beginning to gather these particles, pulling them together to form the first stars and galaxies. This process was the foundation of the universe as we know it. Could these early structures have somehow spawned supermassive black holes? Theories abound, but none fully explain the rapid emergence of these giants. The mystery deepens when we consider the sheer scale of these black holes. Their existence so early in the universe's history is like a puzzle with missing pieces. They are billions of times heavier than our sun. Their immense gravity shapes the galaxies around them, influencing the formation and evolution of cosmic structures. And they formed when the universe was barely 1 billion years old. This rapid formation is akin to a cosmic miracle, defying our current understanding of astrophysics. It's like finding a skyscraper in a newborn baby's nursery. The scale and timing simply don't align with our expectations. It simply doesn't add up, or does it? As we continue to explore the universe, each discovery brings us closer to understanding these cosmic giants. The enigma of early supermassive black holes remains one of the greatest mysteries of our time, a puzzle that challenges our very perception of the cosmos. Imagine a star, much more massive than our sun, reaching the end of its life. This star has lived for millions, perhaps even billions of years, shining brightly in the cosmos. It has burned through all its fuel, exhausting the hydrogen and helium that powered its nuclear fusion reactions. Fusion, the engine of stars, grinds to a halt. Without the outward pressure from fusion, the balance is broken. Gravity seizes control, crushing the star's core with an unstoppable force. The core, once a bustling hub of nuclear activity, now succumbs to the relentless pull of gravity. The core collapses in on itself, imploding in a dramatic and violent event. This implosion is so powerful that it can trigger a supernova explosion, briefly outshining entire galaxies. A black hole is born from the remnants of this cataclysmic event. It is an object so dense that not even light can escape its gravitational pull. These stellar mass black holes are common throughout the universe. They are scattered across galaxies, often hidden from view. They are the remnants of dead stars, the final stage in the life cycle of massive stars, but they are tiny compared to the supermassive ones found at the centers of galaxies. These cosmic giants can be millions or even billions of times more massive than our sun. So how do we get from these small seeds to the cosmic giants? The journey from a stellar mass black hole to a supermassive black hole is a tale of cosmic evolution. One possibility is that these seed black holes formed in the early universe from the collapse of massive gas clouds. These clouds, rich in primordial gas, were the building blocks of the first stars and galaxies. These clouds, instead of forming stars, could have collapsed directly into black holes. This process bypasses the star formation stage entirely. These direct collapsed black holes would have been much larger than stellar mass black holes from the start. They could have served as the seeds for the supermassive black holes we observe today. These seed black holes, whether from stellar collapse or direct gas cloud collapse, are just the beginning. Their growth into supermassive black holes is a complex process involving the accumulation of vast amounts of matter over billions of years. To grow into the supermassive black holes we see today, they need to feed. They need to consume vast amounts of matter, including gas, dust, and even entire stars. They need to consume vast amounts of matter. This feeding process is often accompanied by the release of enormous amounts of energy, making these black holes some of the brightest objects in the universe. And they have just the right tool for the job: gravity. Gravity pulls in matter from their surroundings, allowing them to grow and evolve into the cosmic behemoths we observe in the hearts of galaxies. Black holes are cosmic vacuum cleaners. Their gravity is so strong that nothing, not even light, can escape their grasp. As gas and dust venture too close, they get pulled in, spiraling towards the event horizon, the point of no return. This process, called accretion, is how black holes grow. Imagine a giant whirlpool sucking in everything around it. That's a black hole, feasting on its surroundings. As matter falls into a black hole, it heats up, glowing brightly. This glowing material forms an accretion disk, a swirling ring of light and heat that can outshine entire galaxies.
Accretion is a messy process. Not everything that falls towards a black hole makes it past the event horizon. Some of the material gets flung away at incredible speeds, creating powerful jets that blast out from the black hole's poles. These jets can stretch for thousands of light years, influencing the evolution of entire galaxies. But even with their insatiable appetites, can accretion alone explain the rapid growth of supermassive black holes in the early universe? It's possible. But there's another ingredient in this cosmic recipe: mergers.
When titans collide, mergers, a symphony of destruction and growth.
Galaxies are not islands in space. They are in constant motion, drawn together by their mutual gravity, and sometimes they collide. These galactic mergers are some of the most spectacular events in the universe.
When galaxies collide, their central black holes, drawn together by their immense gravity, spiral towards each other. This cosmic dance can last for millions, even billions of years. As they get closer, they stir up the gas and dust between them, triggering intense bursts of star formation.
Finally, the inevitable happens. The two black holes merge in a cataclysmic event that sends ripples through space-time itself, gravitational waves. These waves carry away energy, causing the newly merged black hole to settle into a new, larger orbit.
Mergers are a key way for black holes to grow rapidly. A single merger can double the mass of a black hole in an instant, and in the early universe, when galaxies were closer together and collisions were more common, mergers would have been frequent, fueling the growth of supermassive black holes.
Galactic Architects: the profound influence of black holes on galaxies.
Supermassive black holes are not just passive bystanders in the evolution of galaxies, they are active participants shaping the galaxies they inhabit. Their influence is felt far beyond their event horizons, reaching out to influence the very fabric of their host galaxies.
One way black holes influence galaxies is through their powerful jets. These jets, blasting out from the black hole's poles, can heat up and push away the gas and dust in their surroundings. This process can regulate star formation, preventing galaxies from growing too big, too fast.
Black holes can also influence the distribution of stars within a galaxy. As they gobble up matter and grow, their gravity can stir up the surrounding stars, creating a bulge at the center of the galaxy. This is why many spiral galaxies, like our own Milky Way, have a central bulge of older stars.
The relationship between supermassive black holes and their host galaxies is a complex and dynamic one. They are inextricably linked, their fates intertwined. Understanding one is crucial to understanding the other. Quenching the cosmic fire. Supermassive black holes and star formation. Supermassive black holes are not just cosmic vacuum cleaners, they are also the regulators of the universe, playing a pivotal role in the life cycle of galaxies.
Star formation is the lifeblood of a galaxy. It's the process that breathes new life into the cosmos, creating the stars that light up the night sky. It's the process by which new stars are born from collapsing clouds of gas and dust. These clouds, under the influence of gravity, condense and ignite to form new stars, continuing the cycle of stellar evolution. But this process can't go on forever. There are limits to how much gas and dust a galaxy can convert into stars. Something needs to regulate it. Without regulation, galaxies would either burn out quickly or stagnate without forming new stars. Something needs to prevent galaxies from converting all their gas into stars and then fading into obscurity. This regulation ensures that galaxies can sustain star formation over longer periods.
That something, it turns out, might be supermassive black holes. These cosmic giants are not just passive observers, but active participants in the galactic ecosystem. As black holes accrete matter, they release enormous amounts of energy. This energy can have profound effects on the surrounding environment. This energy can heat up the surrounding gas, making it difficult for it to cool and collapse to form stars. The heated gas resists gravitational collapse, thereby slowing down the rate of star formation. This process, known as quenching, is thought to be responsible for the relatively low star formation rates we see in many massive galaxies today. Quenching acts as a cosmic thermostat, regulating the temperature and density of the gas in galaxies.
These galaxies are thought to have already experienced a period of intense star formation fueled by their supermassive black holes. During this phase, the black holes provided the necessary energy to trigger rapid star formation. But now, their black holes have grown so massive that they are actively suppressing further star formation. The energy output from these black holes is so immense that it prevents the gas from cooling and collapsing into new stars.
The relationship between supermassive black holes and star formation is a delicate balancing act. It's a cosmic dance where too much or too little star formation can have dramatic consequences for a galaxy. Too much star formation and a galaxy can burn itself out. The rapid consumption of gas and dust can lead to a short-lived but intense period of star formation, followed by a long period of inactivity. Too little and it can stagnate. Without new stars, a galaxy can become a cosmic backwater, with little activity and few new stars to light up the night. Supermassive black holes, it seems, play a crucial role in maintaining this balance. They are the cosmic regulators, ensuring that galaxies neither burn out too quickly nor stagnate without new star formation. Their influence extends far beyond their immediate surroundings, shaping the very structure and evolution of galaxies.